A mathematical function operates like a highly precise engine. It takes a raw input value, passes it through specific operations, and outputs a structured result. To track exactly how they interact, we'll assign the domain, the inputs on the horizontal x-axis, the color blue. The range, the outputs on the vertical y-axis, will be green. When you look at the shape of a function on a graph, you are looking at a strict manifestation of its algebraic rules. To understand how those rules constrain a graph, we need to see what mathematical space looks like before any limits are applied. This brings us to polynomial functions, the architectural baseline of algebra. Because any real number can be squared or cubed, standard polynomials have no algebraic roadblocks. Their domain extends from negative to positive infinity. As these inputs map to outputs, the graph spans the entire horizontal plane in a continuous sweep. This unbroken span is an exception. In most functions, specific algebraic conditions force the mathematical space to break, stop, or fracture. Diagnosing a function's geometry means hunting for the specific algebraic conditions that truncate this infinite plane. The first major constraint appears in rational functions, which are built as fractions. The rule here relies on a mathematical impossibility. You cannot divide by 0. If we set the denominator of any rational function to 0 and solve it, we isolate the exact coordinate where the function's reality breaks down. Look at the equation, f of x equals 1 divided by x. An input of 0 forces an impossible division, tearing the infinite domain in two. The function swoops toward the void, never touching it, creating a vertical asymptote that deflects outputs up and down. We need a notation to describe an infinite plane with a single exclusion. We achieve this using set builder notation. This statement declares x belongs to all real numbers under the strict condition that x does not equal 0. These denominators in rational functions create hard, impassable walls in mathematical space. The second major architectural constraint emerges in radical functions, specifically when dealing with even roots. To yield a real number, the mathematical expression under an even root, the radicand, must remain greater than or equal to 0. If it dips negative, the result becomes imaginary. Here, f of x equals the square root of x minus 2. We find the boundary by setting the inequality. X minus 2 is greater than or equal to 0. Solving this isolates the start coordinate, proving the domain only exists from 2 onward. For continuous blocks of space with a distinct start point, we prefer interval notation. A hard square bracket indicates inclusion, locking onto our starting point of 2, while a parenthesis indicates infinity, pointing endlessly to the right. These radical constraints act as a harsh cliff edge, literally erasing entire regions of the coordinate plane from existence. Up to now, we have tracked horizontal constraints along the x-axis. We apply the same logic to vertical outcomes on the y-axis. A function's range is heavily dictated by the natural structural limits inherent to its specific mathematical type. This graph plots a principal square root function. A square root yields only non-negative numbers, establishing a hard structural floor it cannot dip below. Similarly, even-powered polynomials like x squared hit a turning point, permanently capping their vertical reach and creating an absolute minimum. The range identifies the specific vertical space a function naturally occupies. Once we establish these structural baselines, we can manipulate them. This universal formula acts as an operational matrix, allowing us to precisely shift and stretch any base function's geometry. Variables a and d operate outside the base function, directly impacting the vertical range. Adding a value to d shifts the graph vertically. Positive values slide the structure up, negative values slide it down. Conversely, variables b and c act inside the function. They modify the input before execution, directly impacting the horizontal domain. But horizontal shifting behaves counterintuitively. If we subtract 3 from the input, the entire geometry shifts right. The x value must mathematically compensate by running 3 units higher just to reach the exact same baseline output. Modifying the outside directly moves the output. Modifying the inside forces the entire coordinate plane to shift to satisfy the function's internal domain rules. Let's test the relationship between these structural limits and transformation parameters with a combined case. This is the graph of our foundational radical function, y equals the square root of x, pinned to the origin point of 0, 0. First, we apply an inside horizontal shift, setting our c parameter to a value of 2. Writing x minus 2 forces the entire valid domain window to the right. The function now requires an input of 2 just to begin. Next, we add an outside vertical shift, setting d to positive 3. Adding 3 to the end of the equation instantly elevates the structural floor of the function's range. Tracking a single constrained origin point through these translations reveals the new domain boundary of 2 to infinity and a range boundary of 3 to infinity. Algebraic formulas and inequalities function as architectural blueprints. Every numerator, denominator, and root generates precise boundaries, asymptotes, and structures across two-dimensional space. By observing a function's base structural constraints and combining them with universal transformations, you can confidently predict and control mathematical geometry.